Hi everyone, today's video is twofold. We are going to talk about combustion reactions, and then we are going to look at all 5 types of reactions that we've discussed in this unit and see if we can classify them into different pieces at the very end of the video. But let's talk about combustion first. So, in a combustion reaction, we have a hydrocarbon burning in oxygen. Now, what is a hydrocarbon? Well, a hydrocarbon is made up of 2 elements, hydrogen and carbon. And typically hydrogen comes after carbon, so that's why I wrote it in that order. But a hydrocarbon is simply carbon and hydrogen. And it turns out that hydrocarbons may also include oxygen. So if you have a compound that is made up of carbon and hydrogen and oxygen potentially, always, if they burn in oxygen, they make the same 2 products. The products they make are always carbon dioxide and water. And when they do that, they release a whole lot of energy. So one common hydrocarbon is C3H8. That's propane. You know you can burn propane in a grill, and you can get energy to cook your food. Now there's one little oddball combustion reaction to know about. It's the combustion of hydrogen gas. So hydrogen gas does burn, but there's no carbon in this hydrogen gas, so we can't make carbon dioxide. So if you burn hydrogen gas with oxygen, you simply make water, which is why a lot of people are excited about hydrogen as a fuel source, except that it is very flammable. So it would be, you'd need to figure out a way to transport it safely in order to use hydrogen as a large-scale fuel source. But that's for another day. Let's see if we can predict the products of some of these combustion reactions. And good news, because you have a hydrocarbon, right? Carbon and hydrogen put together, and oxygen, you always get the same products. And they are always carbon dioxide, CO2, and water, H2O. And you'll notice in letter B, even though we have a hydrocarbon that has oxygen, it's still backbone hydrocarbon. So hydrocarbons are allowed to have oxygen. If we burn in oxygen, the products are always CO2 plus H2O. And in letters C and D, we have a hydrocarbon and a hydrocarbon burning in oxygen. So the products in both of those are going to be CO2 plus H2O. And down here again, CO2 and water. And so really the challenge with combustion is balancing. And so when we balance, I'm again going to make the list. We don't have a ton of room here, but we only have 3 elements. So we're dealing with carbon, hydrogen, and oxygen, CH and O. And so let's figure out how many we have on both sides. In letter A, we have 3 carbons on the left. We have 1 on the right. We have 8 hydrogens on the left, we have 2 on the right, and we have 2 oxygens on the left, and we have 3 on the right once we combine the 2 from CO2 and the 1 from water. So this trend of 1, 2, 3 on the right is always going to be the same because we're always dealing with CO2 and water. So our tips for balancing combustion reactions are that you should always, always, always save oxygen for last. Why is that? Because it's by itself, and if it's by itself, then if we can balance everything else, we'll just have a single coefficient to put in front of oxygen and our job will be done. So let's balance everything else. Let's just go in order. To balance the carbons, I have 3 on the left. If I put a 3 here, I will have 3 on the right, but I've also changed my oxygens. I now have 3 times 2 is 6, plus the 1 from water, I have 7. In terms of hydrogen, I have 8 hydrogens on the left. In order to get 8 on the right, I need to put a 4 here. So that does indeed give me my 8 hydrogens on the right, but it also changes oxygen. I have 3 times 2 is 6, plus 4 times 1 is 4. 6 plus 4 is 10 oxygens on the right. And now we reap the rewards of having saved oxygen for last, because if I have 10 on the right, I can simply put a 5 right here, and I will have 10 on the left, and everything is good. All right, let's try letter B. Things are a little bit more crazy because now we have oxygen in the hydrocarbon. Let's start with carbon. There are 2 carbons on the left, 1 on the right. There are 6 hydrogens on the left, 2 on the right. You'll notice I got 6 because I added these 5 and that 1. If you're wondering why they're written separately like that, it's because this OH group is a really common, we call it a functional group, and it's often written together. But it doesn't really matter for these purposes. We can still count up all of the hydrogens. And then lastly, on the left-hand side, I have 1 plus 2. I have 3 oxygens on the left-hand side. I also have 3 oxygens on the right-hand side. So let's go in order. Let's start with carbon. We have 2 on the left. In order to fix that, we are going to need to put 2 on the right-hand side. So I'll put a 2 here, but that also changes my oxygens. I now have 5 because I have 2 times 2 from carbon dioxide plus 1 from water is 5. I need to fix those hydrogens. I have, let's see, 6 on the left. If I put a 3 here in front of water, that gives me 6 on the right, but I've changed my oxygens. I now have 2 times 2 is 4 from carbon dioxide, 3 times 1 is 3 from water, so I have a grand total of 7 oxygens. And now things get confusing, right? Because we have oxygen involved in this hydrocarbon here on the left, right? But if you think about this, we really don't want to put any coefficients in this spot, right? We really don't want anything but a 1 there, because if we change anything there, we are going to change the carbon and the hydrogen, and we're going to mess up all of the work we just did to balance. So ideally, we'll leave this alone. And so if we kind of set this oxygen off limits, we'll save that as its own thing. There's 1 oxygen there. We need a grand total of 7 on the left-hand side. If one of them is here, we need 6 from this to give us 7. So what coefficient can we use? Well, if we put a 3 in front of O2, 3 times 2 is 6, plus the 1 gives me 7, and we are good to go. So if you have a situation where you have oxygen in your hydrocarbon like we did there, it's often good to kind of treat it as its own entity and not put a coefficient in front of that hydrocarbon, or else everything else will go a little bit crazy on you, and it'll get really complicated. All right, let's try letter C. C8H18. So we have, again, carbon, hydrogen, and oxygen. We have 8 carbons on the left, 1 on the right. We have 18 hydrogens on the left, 2 on the right. We have 2 oxygens on the left. We have 3 on the right. Let's fix those carbons first. So we need 8 on the right. We'll put an 8 here. That gives us our 8 on the right, but it also changes our oxygens. 8 times 2 is 16, plus 1 from water is 17 oxygens on the right. We also have hydrogens needing to be fixed, so we'll put a 9 here to give me my 18 hydrogens. Let's be careful with oxygen. We have 8 times 2 is 16, 9 times 1 is 9, 16 plus 9 is 25. So this creates a problem, right? The problem is we have an odd number of oxygens on the right, and we have a coefficient, or I'm sorry, a subscript of 2 next to the oxygen on the left. So there's no number that I can easily multiply times 2 to give me 25. But if you remember back to our balancing video, we said there's a trick. And the trick is to write in the number that does make this work. And that number is 12.5. If I put a 12.5 there, I get my 25 oxygens. And indeed, all of my balancing numbers are correct, right? 8 matches 8, 18 matches 18, 25 matches 25. But we can't leave that coefficient the way it is, right? We can't have decimal coefficients. So what we need to do at the end of the day here is to come back through. We'll do this in purple. And we need to multiply everything times 2. So 1 is going to become 2. 12.5 is going to become 25. This is a lot written in here, but 8 is going to become 16, and 9 is going to become 18. And you can literally just leave it like that. You can show your work by crossing out and showing the doubled number. You do not need to erase. Now, we can confirm to ourselves that that worked if we want to. You don't have to do this step, but if it makes you feel better that this is actually correct, you can. So carbons on the left. 2 times 8 is 16. Hydrogens on the left, 2 times 18 is 36. Oxygens on the left, 25 times 2 is 50. Carbons on the right, 16 times 1 is 16. Hydrogens on the right, 18 times 2 is 36. Oxygens on the right, 16 times 2 from the carbon dioxide is 32. 18 times 1 from the water is 18. That gives you 50. So indeed it does work. Again, you don't have to show that work, but it can prove to you that everything worked out. Okay, let's try one more in letter D. So we again have carbon, hydrogen, and oxygen. Here's C, H, and O. We have 6 carbons on the left. We have 1 on the right. We have 14 hydrogens on the left. We have 2 on the right. We have 2 oxygens on the left. We have 3 on the right. Let's go through and fix the carbons first. 6 on the left. 6 here will give me 6 on the right, but fix that oxygen as well. So 6 times 2 is 12, plus the 1 from water is 13. Let's fix those hydrogens. We got 14 on the left. We need 14 on the right, so a 7 will do the trick. That gives us 14 hydrogens on the right, but oxygen-wise, we have 6 times 2 is 12, plus 7 times 1 is 7. We have 19 oxygens. 19 is not divisible by 2, but it kind of is, right? Because 9.5 would make this work. That would give us our 19 oxygens. But we can't leave that coefficient the way it stands, so we are going to take everything and double it. 1 becomes 2, 9.5 becomes 19, 6 becomes 12, 7 becomes 14. So again, you can get much more practice with that if you so desire, but that's our nice little trick for combustion reactions, is if you can't get everything to balance, try using a decimal with the oxygen, try using half, and then double everything. Now, we're not done, because in addition to having our look at combustion reactions, we also want to work on classifying chemical reactions. And just so you're aware, there's a page down here. It's the 8th page on these notes that you can take a look at. It's also on Canvas if you so desire. It's a nice little flow chart to help you classify chemical reactions. But I think you can actually make sense of this as we go through. So what we're going to do in number 2 here is we're actually going to reverse the order. We're first going to write a balanced chemical equation. Then we're going to come through at the end and classify all of these. So if you want to pause and see if you can review turning these word equations into formulas, we'll do that. And we're going to go pretty quickly here. So if you've paused and you're going to try it, let's stick together. So we have C4H10 in letter A, plus oxygen. We know oxygen's diatomic, so O2. That's coming together to yield carbon dioxide and water, CO2 plus H2O. Now we would need to balance this. When we balance, we have 4 carbons on the left, so let's get a 4 here. We're going to put a 5 here. That's going to be ugly because we're going to have a half. So the half that we would use would be, we now have 2 times 2 is 4, plus 5 is 9 oxygens on the right. We would have 9 oxygens on the left by doing 4.5 there. But we need to double everything, so let's make this a 2, let's make this a 9, let's make this a 4, let's make this a 10. And we'll come back and we'll define what that is in a second. Okay, aluminum plus plumbous nitrate. So aluminum is Al. Plumbous nitrate. Plumbous is Pb plus 2. Nitrate is NO3 minus 1, so that gives us PbNO3 2. Yields simply lead by itself, which is Pb, plus aluminum nitrate. Aluminum's a plus 3, nitrate's a minus 1, AlNO3 3. Again, we are going fast, so if you want to pause the video and try these on your own and then kind of jump back in to make sense of it, feel free. Letter C, calcium carbonate. Calcium carbonate, Ca plus 2, CO3 minus 2, so simply CaCO3, yields calcium oxide, Ca plus 2, O minus 2, CaO, plus carbon dioxide, CO2. Letter D, iron 2 sulfide. Iron 2 sulfide would be Fe plus 2, S minus 2, so FeS, plus hydrochloric acid, HCl, yields hydrosulfuric acid. Remember that hydro means binary, so this is going to be H2S, plus iron 2 chloride, Fe plus 2, Cl minus 1, FeCl2. Then finally we have rubidium, which is Rb, added together with sulfur. And let's check our periodic table, because Rb is one that we don't use very often. So Rb on the periodic table is right here. It's a plus 1. So we have Rb plus 1, S minus 2 for rubidium sulfide. We have Rb2S. Now, we would need to balance all of the ones I've just done in pink, so let's come back through and let's do that quickly. In the second one, we have 3 nitrates on the right and 2 on the left. Lowest common multiple is 6, so we know at a minimum we're going to need a 3 here and a 2 here, and to finish the job we'll put a 2 with aluminum and a 3 with lead. Calcium carbonate making calcium oxide and carbon dioxide is already balanced. In letter D, we have 2 H's on the right and 2 Cl's on the right. Let's put a 2 here to finish the job. And then in letter E, we will need 2 rubidiums to make this thing work out. So what we need to do is classify all of these as either synthesis, decomposition, single displacement, double displacement, or combustion. So there are some hallmarks of each as we go down the list. In letter A, we have a hydrocarbon combining with oxygen. Hydrocarbon combining with oxygen automatically tells us that we are dealing with combustion. So combustion whenever we have a hydrocarbon with oxygen. In letter B, you're going to notice that we have something by itself plus a compound. And when it's by itself plus a compound, you'll notice we make something else by itself plus a different compound. So that is a hallmark of single displacement or single replacement. We would have to check the activity series for letter B, but we're just going to assume this works because all we care about right now is classifying the reaction. In letter C, you have a single thing breaking down. So anytime you have one thing by itself, notice that's different than all of the others. Every other letter has multiple reactants. Anytime you have a single reactant, that is going to be a decomposition because it's one thing decomposing into multiple. So letter C is decomposition. Letter D, we have 2 compounds. Anytime you have 2 ionic compounds, notice ionic compound, we'll call binary acids ionic for now, because we're using a cation in H+. So 2 ionic compounds making 2 different ionic compounds. Anytime you're trading cations, that is a hallmark of double displacement. And then finally, anytime you make a single product, so notice letter E is the only one with a single product, that's 2 things coming together to make one thing, that is the hallmark of synthesis. So just to kind of recap, right, in terms of decomposition versus synthesis, decomposition is the only one that has a single reactant. Synthesis is the only one that has a single product. Single displacement is multiple products and multiple reactants, but it's a single entity plus a compound versus a compound plus a compound. That's what distinguishes single displacement from double displacement. And combustion is an oddball because it always has a hydrocarbon plus oxygen. So again, we want to get some practice with this. We want to be able to look at a reaction and identify which of those 5 types of reactions it is.